Hi everyone, welcome to mini lesson 17. Today we're going to talk about the Debye model of vibrations in solids. And one way to think of this is that we're going to do the statistical mechanics and thermodynamics of a phonon gas in a solid as compared to a photon gas, which was our model of a black body. This is Schroeder's section 7.5. I'm going to more or less follow what Schroeder does. But in some ways, I'll be a little bit more inclined to reason by analogy to the photon gas than Schroeder is. So let's just try to motivate the idea of phonons. So if we accept that photons are particles that represent the quantization of the electromagnetic field, right? We're basically saying that wave-particle duality in quantum mechanics is if you have an electromagnetic wave, there's a corresponding particle we call the photon, right? And so when we think about sound waves propagating through matter, like a chunk of solid, there's a corresponding quanta, and the name that we give that quantized sound wave is a phonon, right? And so if you believe in photons, I claim you are required to also believe in phonons. Now there's a difference between photons and phonons in that photons can propagate through vacuum. Right? Electromagnetic waves can just go through empty space. By contrast, sound waves require a medium. So you can't have a sound wave if there aren't atoms to vibrate back and forth. So you need a gas or a liquid or a solid to have a sound wave. And so that's a difference. And so you might emphasize that difference by calling a phonon a quasi-particle instead of a real particle like a photon would be considered. So a photon is one of the particles in the standard model of particle physics. It's considered fundamental. It can fly through vacuum. A phonon is a quasi-particle, and it's part of the standard model of condensed matter or solid state physics. So this is just a little picture of what you're supposed to think about. A solid is a bunch of atoms connected by springs, and they can collectively vibrate back and forth. And their vibrational modes are the sound waves or the phonons of the solid. So I took this picture from this open source physics site, which has a lot of really cool Java simulations. And so if you want, you can go to this site and you can actually look at some different vibrational modes of this chain of atoms. That's like a 1D solid. It's actually a really cool site for just getting general simulations. And they're all free. And in fact, a lot of them are made by North Carolina people, and some of whom are NC State graduates. So Wolfgang Christian, for example, is a famous NC State graduate student from many, many decades ago, and he does a lot of the simulations. Anyway, check that out. I'll just use that picture as a little reminder of the basic physics picture of what we're talking about. So let's think about phonons in a couple of different ways from the statistical mechanics perspective. So if we take seriously this picture that vibrations in solids can be modeled by thinking of the atoms as just connected by ideal harmonic springs, we can write the energy expression for every atom as a spring potential energy corresponding to the x displacements plus a kinetic energy in the x direction, and then the same for y, potential kinetic, and the same for z. And so if we look at that, energy expression, we have 6 quadratic degrees of freedom appearing in the energy expression. And in chapter 6, we already proved equipartition of energy theorem rigorously. So we know each of those terms contributes a half kBt to the energy of the solid. So each atom will contribute 6 times a half kBt. And if we have n atoms, we get a total internal vibrational energy of the solid as 3n kBt. So this is a clear prediction for how a solid should behave. It predicts that the heat capacity at constant volume for a solid should be the partial of this expression with respect to T, at constant V and N. And so you just get 3 NKB. So it says every solid on a per mole basis should have the exact same constant volume heat capacity. Experimentally, this is not true. Different materials have different heat capacities, and heat capacities actually depend on temperature. This does turn out to be true at high enough temperature. So as you go to high enough temperature, the heat capacity of all solids on a per mole basis approaches the same constant value. And so you can see some data about that in chapter 1. But let's move on and try to do better. So let's think of the atoms as connected by ideal harmonic springs, but now let's think of it in a quantum mechanics picture. So the Einstein model that we developed in chapter 2 and chapter 3, not just chapter 3, basically proposes that vibrations in a solid are best modeled by saying that there's just one kind of spring in the solid. So there's one angular frequency, that's whatever the spring constant is times the mass of the stuff that's vibrating. And so the Einstein model basically says we have n identical oscillators, and then we have q units of energy to distribute among the n identical oscillators. So each one of those units of energy has h bar omega joules, if you want, of energy, so that the total energy in the solid is q, the number of units of energy, times h bar omega, the value of energy in each unit. It's important not to get confused about what q represents and what u represents and what h bar omega represents. So pay attention to this line. So if we've got a 3D solid, each atom can vibrate in 3 directions. So there's 3 oscillators per atom. Or in other words, the number of atoms is equal to the number of oscillators divided by 3. That's also an important caveat. So how do we get a relationship for u of t in this model, which is different than the classical model? Again, so this is sort of a quantum model in that it's proposing this sort of quantization of oscillator energy. And so we can just figure this out by doing S is equal to kb ln omega, where omega is the multiplicity of the Einstein solid expression. Again, go back to chapter 2 for this. And once you've done that, you can calculate the temperature by applying a thermodynamic definition of temperature, partial U with respect to T at constant V and N. So I'm pretty sure this was a question in test 1 to sort of go through and mess with this a little bit. It's something that I really think you should be able to do in this class. I probably won't give you the exact same question again, but I might give you a variation on it. And so the thing I'm looking for when you're applying this is I want to see that you know how and when to use baby Stirling, and how and when to use the Taylor expansion of log 1 plus x is approximately x. That equals sign is supposed to be a plus. Hopefully that's obvious. That was my typo. I'm not going to refilm for that. So let's combine with this definition of temperature, making this correct substitution so that we actually have a function. What the heck is this? Yeah, so that's an incorrect definition. This is supposed to be du ds, not du dt. This expression doesn't make any sense. I think I maybe won't refilm this. So let's see if you can pay attention and see where this needs to be changed and why. So it's interesting to go ahead and see if you can derive this expression for constant volume heat capacity. Not super hard, very good practice. You know, the skills that you get by practicing this are the skills that I will be looking for on final exams. But let's just take a look at this formula and see what we get. So let me say that I think the oscillator energy is 0.01 electron volts. All right, and so if I plug that in, I get this blue curve for the Einstein heat capacity as a function of temperature. And I can go in and define an Einstein temperature as the oscillator energy divided by kb, the Boltzmann constant. And that's about 116 Kelvin. So it should start to feel really familiar to you that when you're given an energy scale, you can define a temperature scale, and vice versa. Okay? So it's really important that this is not mysterious to you why I'm doing this. Interestingly, there is only one energy scale in the Einstein model, and it's h bar omega. Okay? And therefore, you know exactly what energy you need to use to think about a specific temperature scale. So there's only one here. In some problems, there might be two or more. That gets to be difficult to deal with, but also really interesting. One of the big challenges in any physics problem is to identify what is the important energy scale, and that also implies an important temperature scale, right? And so in this problem, it's really easy because there's only one thing you can choose. And so I marked that here, and it turns out it sort of looks like the place where the CV as a function of temperature curve has started to be really flat. So at low temperatures, CV is really, really rapidly increasing with temperature. And if you take a low temperature limit of this, you'll find out that it's exponentially increasing with temperature. Okay? It's basically like e to the minus e over kb, epsilon over kBt. Right? But then above this characteristic temperature, the Einstein temperature, the value is really approximately that given by the classical number of 3 nkb. And this was particularly done for n equals 1 mole. Right? So below T sub e, we have basically quantum effects, giving you a strong dependence of CV on temperature. And above T sub e, we're really classical. And we just have this classical equipartition result. So the problem with the Einstein model is that there isn't just one oscillation frequency. There are all kinds of different oscillation frequencies inside a solid. So hopefully that's intuitive that there could be different oscillation frequencies. But even for this one-dimensional case, you can go in and see that there are just different ways that these atoms can vibrate with different frequencies. And so the Einstein model misses that. It's not a completely ridiculous model because for many physical circumstances, there's one oscillation frequency that you really, really care about. And so in that case, the Einstein model will be really good. But it's not perfect. And so the way that we can go about treating situations where there are a range of oscillation frequencies is we can do the same thing that we did for blackbody radiation. We can say that we've got a solid which is now a box of wave quanta. So they're bosons. And let's just imagine that they're an ideal gas of bosons. Instead of being photons, they're phonons. All right? So the black body was considered as a gas of photons. And an ordinary solid where we care about the different vibrational frequencies is a gas of phonons. And that's the Debye model. So the only distinction, well, not the only distinction. An important distinction is that if we drilled a hole in this solid, we could imagine photons being radiated and collecting them with a spectrometer to see their spectrum. You can't do that with the vibrations in a solid. They can't leave because there's no atoms to vibrate out here in vacuum. There are a number of differences that we're going to need to focus on. So we did a lot about the photon gas this week, and so we're not going to let that go to waste. We're going to use it every single time we can. So what we need to do is just point out the key differences where we need to change our model to correspond to phonons instead of photons. So number one, the speed of sound is different than the speed of light. So the wave speed is different. That's obvious. Number two, phonons have 3 possible polarizations. So electromagnetic waves have to be transverse waves. In other words, the E and B fields always have to be perpendicular to the propagation direction. That's just set by Maxwell's equations. The phonons don't have that restriction, so you can have a longitudinal wave in addition to a bunch of transverse waves. So we have to have 3 polarizations for phonons instead of photons. In some ways, I consider these 2 differences to be trivial in the sense that that's going into the photon model and just changing a number. And that's not really an important change. That's just like, okay, use the number 3 instead of the number 2, or use the speed of sound instead of the speed of light. Otherwise, the model is identical. The third difference is really non-trivial in that you change a really important physics piece of the model. And that is, phonons have to have an upper limit on their energy. So for a light wave, you can have wavelengths that are arbitrarily small. You make smaller and smaller wavelengths, the energy of the light wave goes up and up, right? You're going from the visible to the UV to the X-rays to the gamma rays to the super, super high energy gamma rays. You can just keep going. There's no restriction. In a solid, the wavelength is constrained by the atomic spacing. You can't have anything smaller than, say, half wavelength equals to an atomic spacing, right? And this is a really key step in the model that we need to install. So here's how we do it. In our expression for internal energy, we have a prefactor of 3 that comes from the polarizations. We use the speed of sound instead of the speed of light. But then the really important non-trivial change to the model is that instead of integrating from 0 to infinity, we need to integrate from 0 up to some maximum phonon energy, right? So this is exactly the integral expression for U that we used for the photon gas, except we've basically gone and plugged in these 3 changes. That's not hand waving. That's me not wasting time repeating the steps that I did before. So the really hard question, and the reason that that phonons in solids are really different than photons in a black body, is we need to figure out what's the upper limit to this integral. So we definitely can write out the energy in the same way that we did for the photon energies. It's h times the speed times n max over 2L, where L is the side length of the solid or the box. In this case, n max defines the radius of an octant of a sphere in nx and y and z space, again, just like we did for the photon gas. But the key point is that because we're in a solid, we need to have 1 atom per value of n. And so just to understand this, this is sort of related to that connection between the wavelength of the sound wave and the atomic structure of the solid. And Schroeder has a good picture 726 that shows sort of why that has to be so. But roughly speaking, the volume of this octant of the sphere has to equal the number of atoms in the solid. And that gives you a condition on E max that relates the maximum energy to the number of atoms in the solid, geometry of the solid, and the speed of sound in the solid. This is kind of an approximation in that to do this correctly, it wouldn't actually be a sphere. It would be more like a cube. Or if the solid really had low symmetry, it would just be an arbitrary parallel pipehead. But we're not going to worry about those differences in solid state physics effects. We're just going to sort of say, okay, it's about like a sphere. And the differences will sort of be small numerical factors out in front of the integral. So we go in with this E max value and substitute for an X max, where X max is E max over kBt. And I'd like to do the thing that we did before for the Einstein model and say if there's an E max, we can write that out as a kb times a T max, so that the kb's would cancel and X max is some maximum temperature divided by the actual temperature of the solid. And so we call this maximum temperature the Debye temperature for the Debye model. And we can go ahead and plug in T Debye is equal to this expression, which is just related to physical properties of the solid. So in particular, if you have a large speed of sound in the solid, you have a large Debye temperature. And so, again, I want to point out that what we've done here is to identify a key energy scale in the problem. And that's typically a difficult part of doing physics, is to go into the physics problem and say, is there one special energy scale in this problem? And in the Debye model, it's difficult because we're saying we have a whole continuous range of energies of phonons available, right? They have a density of states that goes as energy squared, and they're a continuum. But because of this special fact that there must be an upper limit to the energies, we do identify a clear characteristic energy scale and associate to that this Debye temperature. And so if we want to really focus our attention on the most important physics in this problem, we're going to bring that key energy scale front and center. So we're going to try to rewrite our results in terms of the Debye temperature in order to focus on this key scale. And so we do that this way. You do a bunch of substitutions. Please try them yourselves. They're straightforward. But you can actually write that integral out as the internal energy is 9 times the number of atoms in the solid times kBt to the fourth divided by Debye temperature cubed. And then you integrate from 0 to x max this function. You can't do this integral in general, right? This isn't, if it was 0 to infinity, this integral would be something we know. I'll say that in a second. But in general, this expression just has to be dealt with numerically. So the way that we're going to work with it is by taking high and low temperature limits. So in the low temperature limit, we mean that the temperature is much less than the Debye temperature. And what that means is x max is much, much bigger than 1. So let me go back a slide. All right, x max is T Debye over T, okay? T Debye over T in the upper limit. And so if x max is much, much bigger than 1, we're just going to set the upper limit to infinity, just like for the photon gas. So then that integral has a known value of pi to the fourth over 15. And so you get the internal energy as this expression, and the heat capacity is this expression, right? So at low temperatures, the phonon gas is almost indistinguishable from the photon gas, except for the trivial changes of subbing in the speed of sound for the speed of light and 3 polarizations instead of 2. And this is something you can really measure in solids. So the heat capacity in solids at low temperatures very often looks like it's growing with temperature as T cubed. And so that's good evidence that the Debye model is mostly correct. So I just want to point out this crackpot idea. For the photon gas, we assume there was no upper limit to the integral, but what if there was, and we just don't know it? What if there's an energy scale associated with the propagation of photons in vacuum that corresponds to the energy scale associated to the lattice spacing in solids, right? So what would you say would be that energy scale? How would we search for it? Right? So in other words, we have a U goes like T to the fourth for photons, and we say that applies all the time. But what if there's an energy scale where it breaks down? That would be pretty cool to think about. It's a crackpot idea probably, but maybe not. Maybe one of you can come up with some experiment to test it. Let's do the other limit now. Let's do the high temperature limit of the Debye model. And the result here is going to end up being simpler, but the path to the result is a little bit harder. So we'll use this expression. And so now we want to say temperature is much, much bigger than the Debye temperature. And so that means x max is much less than 1. So the upper limit here is much less than 1. So there's nothing we can really do with the upper limit. We just have to keep calling it x max, But if x max is much less than 1, and we're integrating x from 0 up to some number much less than 1, we automatically know that whatever the x values are in this integral under these conditions, they're also very small. So we don't want to just let x go to 0, because that basically means integral from 0 to 0 is 0. That's not right. I mean, it's right, but it just gives us no answer. It says u equals 0. U does go to 0 as temperature goes to 0, but that's not the answer that we want. Sorry, as temperature... Wait, what am I saying? Yeah, it's actually complete nonsense, right? If you would just let x go to 0, this tells you u goes to 0, and that's completely wrong, because we know u should grow strongly with temperature, and it's not going to like turn around and go to 0. Anyway, so yeah, you have to be careful about just subbing in values. What we need to do is do a Taylor expansion. So let's note that x is small, and let's Taylor expand e to the x as 1 plus x. And sub that into the denominator, you get that the internal energy is approximately all this junk times the integral from 0 to x max of x squared. And so you go ahead and get the value x max cubed over 3. And when you sub in the value of x max in terms of T Debye, you find that this expression just becomes the 3 nkb, which is exactly our classical result for heat capacity of a solid at high temperature. So the Debye model gives us everything we want. It says that at low temperatures we have cubic growth, which is not exactly the exponential that you had in the Einstein model, but it's still a strong growth. At intermediate temperatures we actually can't do anything. We just have to treat the integral that we derived numerically. But then at very high temperatures we recover the constant value that we expect from classical equipartition analysis. So that's a pretty cool application of the stat mech that we derived just with some physics tweaks that gives us a totally different result. So if we were looking at this for a photon gas, we would see that heat capacity was growing cubically for all temperatures. And so then my challenge was, well, what if there was some temperature that was super duper duper hot, like maybe Big Bang levels of hot, where suddenly the heat capacity of the photon gas turned over and became flat. All right, so that's the end of our discussion of weird chemical potential equals 0 boson gases. So we did photons and phonons. And in the next lectures, we're going to do more applications of Bose-Einstein statistics, but this time for situations where we have real atoms instead of photons or quasi-particles, phonons. So see you next time.